All right, time to get chapter 11 started. Chapter 11 delves into fluids. We're still dealing with forces. We're now going to deal more with pressure, which we kind of saw a little bit in chapter 10. But it's all things fluids in chapter 11. Okay, so we start off with something that you have learned in chemistry or something in high school, I can guarantee you, and that's density. Mass density to be exactly, because there are all sorts of densities out there. There's mass densities, area densities, linear densities, and we will see some of these on later chapters. But for now, we have mass density. It is represented by a Greek letter, which is a rho. That's how this program makes the rho, but I usually put tails on mine. This is a rho, and it stands for density. And it's mass divided by volume, at least for mass density. Uh, Sometimes you'll see objects with reference to what's called specific gravity, which is basically the density of the substance with relationship to water. So water would have a specific gravity of 1, whereas like uranium would be somewhere in the teens, because it's so much more denser than water. Um, so those are kind of the two things you really need to know about density. Most of this, I imagine, is a review from other classes. You will have a problem on density. Most of you are able to figure it out already because you've seen this stuff multiple times. All right, now new stuff. Pressure. Um, Basically, we have a new equation. It's the hydrostatic equation. I can kind of show you sort of where it might come from. We learned last chapter that pressure was equal to force divided by area. And we know that in the atmosphere, your force is simply your weight, and divide that by your area. Okay, but what if we don't know our mass? Well, I know that density is equal to mass divided by volume, so rho v is equal to m. This is pretty common. A lot of times in fluid applications, you don't have mass, and so you just write rho v for the density times its volume, because are able to measure the density and you are able to measure the volume. You just don't know the mass. And so if I make that substitution, P is equal to, and I'll put in parentheses and say, hey, I substituted this, rho v g over a. And then I'm going to rewrite that as rho g v over a. Well, volume is nothing more than an area times a height. Think of a cylinder. Or think of a circle. The area of the circle is, well, pi r squared. But if you want to get the volume, you would then multiply it by the height. This is a terrible cylinder, I'm fully aware, in order to get the actual volume of that cylinder. And so if we know that volume is area times height, then I get equals rho g, and then this will be a times h over a. We get rho gh. And this is what's known as your hydrostatic equation. It'll give you your pressure in a fluid based off of the depth, or in the case of an atmosphere, height. And it's kind of useful in that regard. Normally, you will see this written as, instead, delta P is equal to a negative rho g delta h, because the only two factors, the density is generally constant. Okay, let me put it this way. The density in this class is going to be constant. The gravitational acceleration is constant, more or less. It's the height that's going to affect the pressure. So those are only two changes. The negative, why I put a negative there, because it generally associates with a negative change of height is an increase in pressure. How so, you say? Well, look at this. This is a beautiful, I believe this is height over here. This is temperature down here. Not really good. Down here. And then over here is your pressure. Notice that as we go down from the thermosphere into the ionosphere, into the stratosphere, and then finally into our troposphere, that the pressure continually increases. So when you have a decrease in height, we have an increase in pressure. So that negative just shows you that it's equal and opposite. Well, no, not equal opposite. That's a terrible word to use. They're opposite of each other. There we go. You will generally just use that delta P is equal to rho GH, rho G delta H. That's normally what I'm going to do, because your book doesn't use the negative, and that's fine. As long as you kind of know the direction that you're going and what you're kind of looking for, it's not that big of a deal. But the true hydrostatic equation, like, I used to be a meteorology major a long time ago, and I took a meteorology class that involved calculus and things like that, but that was the hydrostatic equation they gave us. One other thing that I need to mention while I am on here is pressure gauge. Basically, put, if I expand this out and using your book's labeling, is you have, if you have a pressure minus the atmospheric pressure, and then that's equal to rho GH, this P2 is called your gauge pressure, which I always have to look up how to spell because I can't spell gauge. The gauge pressure is just basically kind of the pressure with respect to atmospheric pressure. It shows you how much it differs from the overall atmosphere. So like your car tires would be a certain amount above the regular atmospheric pressure, since if they were atmospheric pressure, they'd be flat. And so if a question asks you for gauge pressure, that's what it's actually asking you for. All right, so let's do a problem. So we have a diver, and the diver is Holy. If you don't know Holy Diver, it's a song by Dio. Dio is I think it was part of Black Sabbath back in the day. But there was a great cover by Killswitch Engage in the 90s, by the way. But anytime I do a problem about a diver, it has to be a Holy Diver, and then I have that song in my head. But anyways, so we have a Holy Diver, and it takes a breath from an air tank, abandons it at the depth of L, and then rises to the surface, experiencing a pressure change of 9.3 kPa. So your pressure is generally going to be expressed in kilopascals, just because 93,000 or 9,300 is a little long. But anyways, at what depth did she start from? So we wanted to use the fact that it's the change in pressure is equal to rho G delta H. Now, something I didn't point out, but there is a table of densities in your book. Also, it would give you a density in the problem. And the density, and we are, let's see here. I didn't specify, amazingly, but we will today. So in the song, it says, Holy Diver, you've been gone down too long in the midnight sea. So we're going to use seawater. The density of seawater, I believe, is 1023. I'm going to double check that because sometimes it's a little bit off. Where's my seawater? Where's my seawater? Where's my seawater? Oh, crap. We're going to go to 1023 because it's close enough. And that'll be 1023 kilograms per cubic meter. So we use, and like in chemistry, they use grams per milliliter. We use kilograms per cubic meter just because we deal with larger stuff. Regular water, by the way, wow, talking, is equal to 1,000 kilograms per cubic meter, which makes sense. Seawater is a little bit more dense than regular water. So we're going to do seawater because it says he's been down too long in the midnight sea. Oh, what's become of me? So we'll say, okay. Our change in pressure is, we'll just use absolute values. Oopsie. So 9.3 kilopascals, so that's going to be 9,300 pascals, which remember is a Newton per square meter, equals the density of water, 1023 kilograms per cubic meter, and G, which is 9.8. Calculator. So 9,300 divided by 1023, divide that by 9.8, is only 0.93 meters. What this means is, if you literally do this from only about a meter, so about 3 feet, you could potentially rupture your lungs just because, as basically put, when you're a meter down below the ocean, it's 9,300 pascals higher than the atmospheric pressure. So if you were to take a breath of air, like a huge breath of air, and then abandon your tank and then rise up, your lungs are already at maximum capacity. And then the outside pressure around you ends up decreasing, and your lungs can literally expand and rupture. So this is something you should never, ever, ever do, but this is also a classic problem you can find in well, your physics doesn't have it, but a lot of physics textbooks have this one. So most people don't get in a situation where they're going to be breathing in a huge hunk of air about 3 feet below the water, but it is possible that it can potentially hurt you. Definitely, if you're at a Olympic swimming pool, even just regular fresh water, and you were to breathe literally at the bottom and then rise all the way up, it would probably kill you. So, anywho, if you take diving classes, they teach you how to like breathe out on the way up so that you equalize with the pressure. I've never had diving classes, but usually there's at least one person in the class who kind of knows what I'm talking about, at least with regard to this. Anyways, Holy Diver, fun times. All right, so let's do a slightly different problem. We have a hiker with, let's say, an altimeter, records a pressure change of 9.3 kilopascals. If the elevation of the base of the mountain's around 5,300 feet, so 16.5 meters, how high up is the hiker now? Okay, so we're also looking for H. So we're going to use delta P is equal to rho GH. A little bit more math here. This one is dealing with air. And so we will need to look up the density of air. I believe your book uses it as 1.23. I found water over here. There's 1,000. 1.29 is what they use. Sorry, I'm glad I looked that up. So 1.29 kilograms per cubic meter. So we'll use that as the common density of air. And we want to figure out the new height of the hiker. Okay, so once again, we have the same thing, 9,300 pascals equals our density, which is a different density of 1.29 kilograms per cubic meter, G, 9.8, H. So 9,300 divided by 1.29, divide that by 9.8, gives me a height change of, that's bad, a height change of 700, and let's round it to 36 meters. Now it wants to know the absolute elevation, and so we started at 16.5, so I add that to my 736, and you get around 2352. And in feet, that gives me 7715. Just to give you kind of a scale factor. So an altimeter, now that we have GPS, no one really uses altimeters anymore, but altimeters would use the change in atmospheric pressure to kind of give you an idea of how high you are. They weren't 100%, but they're pretty close. One of my first altimeters, or rather height measuring devices, was an altimeter when I used to go hiking. And it can be affected by other things, like if you're hiking and all of a sudden a storm goes through, well, that's going to affect your altimeter because it's going to lower the pressure. So it only works like if you got really good weather that day. But that's how we used to measure the height, and then you can kind of get an idea how high you climbed. Not so much nowadays. We just have a little GPS, and GPS does everything for you. Kind of takes the fun out of it. All right. Pascal's principle is kind of a unique equation. But Pascal's principle says that any change in pressure applied to a completely enclosed fluid is transmitted undiminished to all parts of the fluid and enclosing walls. This one does not, while air is a fluid, air does not apply for Pascal's principle. because air can be compressed, which I maybe should have put that word in there. Basically, a non-compressible fluid. Any change in pressure to a completely enclosed non-compressible fluid. There we go. Well, I mean, that kind of makes sense. If you put pressure on one end of a water balloon, then the other end of the water balloon is going to grow. But the very fundamental principle is that your pressure at one point is going to equal your pressure at another point in an enclosed fluid that's not compressible. Well, we know that P1 is nothing more than F1 over A1, and we know that P2 is nothing more than F2 over A2. And so this is the equation that we're going to use. Now, the handy thing about that is you could have a force over a small area lift up something large over a larger area, and you could essentially, if you're not strong enough to lift up this weight set, well, you set up a system of hydraulics, and hydraulics will lift it for you, just due to the way of an enclosed fluid, the fact that it's not compressible and how an enclosed fluid works. So by changing your force, or sorry, by changing your areas, you're able to lift up a larger force, since we know that F1 over A1 is F2 over A2. And so that's kind of the unique thing about Pascal's principle. If you ever go to a barber shop, some of the older ones used to, I think they still use some sort of, some of them are pneumatic, but I think some of the older ones use hydraulic systems. There's hydraulic brakes in some types of bikes, if I remember correctly. And there's hydraulic lifts all the time. So, anywho, so let's do a hydraulic problem. Donnie Deathcore is 222 pounds at 100 kilograms. And he sits in a barber chair. We're assuming it's a barber chair with hydraulics. The piston underneath his seat has a diameter around 10 centimeters. If the area under the foot pedal is around 6 times 10 to the 4th meters squared, roughly 6 centimeters squared, how much force will need to be applied to lift Donnie up? Okay, so we got to use Pascal's principle, which is F1 over A1 equals F2 over A2. We'll call Donnie Deathcore F1. Well, rather, his weight is going to be F1. So that means that the area, this will be A1, and then this is going to be A2. So we're going to look for F2. So I'll solve this for F2. That gives me F1 A2 over A1 equals F2 equals force of 1. So it's the weight of Donnie. So that's going to be 100 kilograms times 9.8. And then the area of the 2. So that's going to be the 6 times 10 to the negative 4th. Or 6 centimeters squared. 6e negative 4 squared. And then all over the area of 1. So it says the diameter is 10 centimeters. So we would need the radius of 5 centimeters. So this will need to be pi r, which will be 0.05 meters squared. So let's do some math here. 100 times 9.8 times 6e negative 4. And then divide that by pi. And then divide that by 0.05 squared. And I get 75 newtons. Give me a second. I want to do one more quick calculation. Okay. So what that means is you have Donnie Deathcore is 980 newtons, right? But you only need to apply 75 newtons in order to lift him up. Way, way less force than needed to. And the difference between the areas is this one was 6 times 10 to the negative 4th meters squared, but the other area is 7.85 times 10 to the negative 3rd meters squared, or if we use the fact that this is centimeters squared, that's actually going to be 78.5 centimeters squared. So the area is larger. So as long as your force is over a smaller area and then the bigger object has a larger area underneath it, with a compressible fluid and using hydraulics, you can actually lift heavy objects, which is kind of fun. So that's kind of the unique thing about that. All right, Archimedes' principle is that the upward force exerted by a fluid is called the buoyant force. Actually, that's not Archimedes' principle, but it gets to Archimedes' principle. This buoyant force is kind of cool. It is the inherent upward force on an object in a fluid, particularly water, was what we mostly deal with. And it's really hard to visualize. But luckily, some new research was done that kind of shows you a really, really freaking cool visualization. Let me see here. Okay, so basically, these researchers would vigorously shake a fluid. It wasn't actually water. It was like glycerin or something like that. Or actually, it wasn't glycerin. I don't remember what. Basically, it was a fluid that wasn't water. And they had a machine that would shake it vigorously. And so basically, by doing this, you could levitate the water. And then since you could levitate the water, you could put objects in it. So this is what they did. So, I mean, that's why it's shaking back and forth. But we have two toy boats. There's a boat up top and a boat in the bottom. And notice that the boat on the bottom is still going up. It's not falling down. That's because the buoyant force in the water is holding it up, and it's actually stronger than the gravitational force. You don't see this on a daily basis because we don't exactly have, equipment at the local lake that's going to do this. But yeah, really kind of cool. That's your buoyant force. And so that's a good example of showing you the buoyant force that it indeed does exist. And it's not just like an equal and opposite force of gravity, and it's playing things for me. So the buoyant force is actually equal to the weight of the displaced fluid. This is something I always screwed up on, and maybe to this day I probably screwed up on. It's equal to the weight of the displaced fluid. Meaning if you have a cylinder and it's at a level of 10 milliliters, and then you put in an object, and then the cylinder is now at 20 milliliters, it's equal to the weight of 20 minus 10, the displaced fluid. And basically, Archimedes was able to find that you could find the weight of objects by using the displaced fluid, because he discovered that the weight of the object was equal to the weight of the displaced fluid. Another way of looking at it is the mass of the displaced fluid is equal to the mass of the object, assuming the gravitational constant is the same. Now, there is kind of a float-sink equation you could come up with. And so basically, let's say I have some water. Oh, I know what we could do. Let's make it colorful, because I can do that. Blue! Haha. You like that, don't you? Probably not. I do, though. Alright, so we have an object in the fluid, and there is a buoyant force pushing it up, just like that little toy boat, and the weight is going down. And so from, say, chapter 4, we know that the net force is going to be equal to the buoyant force minus the weight. Okay. So a couple things here. We know that the buoyant force is equal to the weight of the object, mg. And we also know that m is equal to the density times volume. So we can express the buoyant force as rho vg. So a general sink float equation is rho vg minus mg, where this rho is the fluid. Of course, this is the displaced volume and gravitational constant. And so this is a float sink equation that we might use occasionally. But this kind of shows you how something will float. As long as rho vg is higher than the weight that you have, your object is floating. Now, to put that into somewhat action, um, we have a spherical balloon, helium, has a radius of say 12 meters. It's a pretty big balloon, but hey. The balloon in the basket has a mass of 196 kilograms. We want to know the maximum mass that the balloon can support while still being able to float. The density of helium is 0.179 kilograms per cubic meter. All right, so here we go. I'm going to use that equation. We have F net is equal to rho Vg minus mg. Okay. All right. So we need to figure out the net force, but what we're looking at is that we want this to be just greater than, or at least at the point where it's neutral, it'd be greater than or equal to rho. Yeah, that was bad. Rho Vg minus mg. All right, so let's figure out what we need to do with this. Okay. We'll just call it equals, but we know it really needs to be greater than, okay? So we're just going to define that there. All right, so we have rho Vg. This is for the air it's displacing. And then we have minus m. And I'm going to separate something here, and I'll show you why. We'll call it balloon mb g minus mheg. Where did this come from? Well, helium has mass. I mean, we think of it as floating, so it doesn't matter. Well, it does float. I mean, it's lighter, or rather, it has a smaller density than air, but it does have mass. So we do need to account for the mass of the helium. The balloon and the basket we put together, because I said it's 196 kilograms. So there's a big factor. We need to factor in the mass of the helium. Okay, so let's try. So we're trying to look for the maximum mass. So basically, whatever this is equal to, this net force, it'll be the maximum weight that's going to be able to hold. And what we can do there is calculate the mass. So it needs to be over that value, obviously. Well, these two equations earlier was if just getting it to float. In this case, we want to know how much it can float. Should have been clear on that. All right, let's try to plug in some values and see what happens. Okay, density of air is 1.29 from previous slide, kilograms per cubic meter. Volume. We're just assuming it's the volume given of the balloon, which is going to be 12 meters. A spherical, so the volume of a sphere is 4/3 pi r cubed. That's really bad for. And the radius is 12. So that's rho v g is going to be 9.8. I'm just going to put a g in here because I'm going to run out of room, and I just realized that. Sorry about that. Minus the mass of the balloon in setup, 196 kilograms. G minus. Okay, here's the issue. We don't know the mass of the helium. We don't. But we do know that the volume of the helium is about the same as the volume of the balloon minus that small little amount of material. So what we could do is we could take the density of the helium and then multiply it by the same volume times G. So I'm going to come down where I have more room so I can actually I still don't think I'm going to be able to. I can pull out G. Ha! That'll help. All right, good. So equals 9.8 meters a second squared inside, go. 1.29 kilogram per cubic meter. 4/3 pi. That's a bad pi. Bad pi. Pi 12 meters cubed. All right, and then minus 196 minus density of helium, 0.179. times 4/3 pi 12 meters cubed. Got it all in there. Woo. Oh, close it off. Good. All right. All right, here we go. 1.29 times 4. Divide that by 3, times that by pi, times that by 12 to the third. And then I'm going to subtract 196. And then I'm going to subtract, in parentheses, 0.179 times 4 times pi times 12 to the third. Too many parentheses. Need to add one more. And then divide it by 3, because I'm afraid it's going to divide my exponent. So close parentheses, divide that by 3. Close parentheses again. Gives me 7845 times 9.8. Alright, so that gives me 76,888, so a lot. Now granted, that's newtons, and we need to figure out the actual mass, and so I probably shouldn't even multiply by 9.8, but then we divide that by 9.8, and that gives me 7,846. So quite a bit, but that's an actual absolutely huge balloon. So this is just an application of how you can use Archimedes' principles. There's all sorts of different types of problems, but this is just one of them. Okay, a classic problem. What fraction of the volume of an iceberg floating in seawater is visible? If you recall, before I start this, the density of ice was equal to 917 kilograms per cubic meter. All right, so how do we get a fraction? Okay. All right, let's start off with Archimedes' principle. We know that the mass of the object is equal to the mass of the displaced fluid. And we know that mass is density times volume. So the density of ice, also I'll put I because we're dealing with ice, times the volume of ice, Vi, is equal to density of the fluid times the volume of the fluid. Okay. Now I know that if we're looking for a fraction of the ice above sea water, we're looking for, say, the absolute value of the volume of ice minus the volume of the fluid divided by the volume of the fluid, since it's kind of like a percent air, but we're looking for percent exposed in this case. And it's actually an absolute value because, well, we're just looking for the positive here. Okay, what's that you leave me? Well, okay, let's do this. If I break this up, this will give me VI over VF minus VF. Sorry, no, not VF. VF over VF is 1. Whoopsie. Boom. There we are. Okay, and then VI over VF, if I bring this down, is going to say, okay, VI over VF is going to be rho F over rho I. And so we're going to substitute this into that. And so it's going to be rho F over rho I minus 1 absolute valued. Now we have something to work with because we do know the density of our fluid and we do know the density of ice. So this will be 1023, and I'll leave out the units because I know they're going to cancel, over 917 minus 1. So 1023, try this one more time, divided by 917. Uh-oh, I said 4, didn't I? Whoopsie. Some books use different values. Close enough. But we're going to use 1024 because that's what I wrote down. Apologize. So 1024 divided by 917. And now I'm going to subtract 1 from that. And that gives me around 11.7%. This is a very not very. It's a pretty constant value. So any iceberg that you see, so I was off the coast of Newfoundland and I saw this iceberg and took its picture. This iceberg, I'm only seeing around 11.7% of it. 12, basically somewhere between 11 and 12%. Now, granted, we did this for only seawater, so if it's like, say, not really quite an iceberg, but an ice hunk floating in, like, say, a lake up in Alaska, it's going to be a little bit different since the density of that water is going to be less since it's freshwater. But you can pretty much be guaranteed you're only going to see somewhere between 11 and 12% of the iceberg because the rest of it's going to be underwater. So this is why it's a classic problem. It could give you a really constant value. So if you ever get a chance to go up to, say, Greenland or Newfoundland, or I'm told that one time an iceberg made its way all the way to Bermuda before melting, maybe Bermuda, you can actually say, oh, I'm only seeing roughly 11-ish% of that iceberg. So kind of cool. All right, fluids in motion. Before we were dealing with steady fluids, so the fluids were static, not going anywhere. Now the fluids are going to go somewhere. They're going to move. There are two types of flow, steady and not steady. Steady flow is obviously the velocity of the fluid is constant. If the flow is extremely steady, we call it laminar, and it follows what's called streamlines. Kind of give you an example of this is try to find a YouTube video that showed this. Here we are. Alright, so this is just a video that kind of shows you both types of flow. On the left is your laminar flow. Generally it follows streamlines. Dang it, went a little too fast. I want to talk more about it. And then on the right is turbulent. Notice with your turbulent flow, you can't really see much of it. It's just kind of all over the place. This is like a faucet on high, whereas laminar flow would be like a faucet on very, very low, and you can kind of see it all hold together. The streamlines are generally these little wisps. Basically, you could think of a very, very shallow creek and then putting a little dye into the creek and then watching it follow these streamlines. These are all examples of laminar flow. Turbulent is obviously like a muddy river or something like that, so it's usually pretty easy to keep track of. Going back. So, two types of flow. You have unsteady and steady, and if it's very steady, we call it laminar flow. We don't see a lot of laminar flow in our life. We usually just see mostly turbulent, but those are some examples of at least what it looks like. Fluids can be compressible, and some fluids are not compressible. Air is a compressible fluid, whereas water, just water in this case, is incompressible. When we're going back to Pascal's principle, we sometimes say fluids are used in hydraulics, but we need to be specific that incompressible fluids are used in hydraulics. Because if we put in air, air can be compressed, and then it becomes a pneumatic. Like a pneumatic door hinge or something like that. You kind of have to know the two differences, the compressible and not compressible. Viscosity kind of more shows up at the end of the chapter, but it's resistance to flow. Viscous flows are slow and very thick, whereas non-viscous flows are fast and thin. Your non-viscous flows are like oil, vinegar, or not really oil, more like water, vinegar. Oil is kind of somewhere in between. It's got a little bit higher viscosity. Honey, molasses, glaciers. They are very, 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 very viscous. They take a very, very long time to flow. So the higher the viscosity, the more resistance it is to actually flowing. Some flows are rotational, meaning they spin, while other flows are irrotational. They just kind of go in a forward direction. And more important and more fun is a lot of fluids are Newtonian while others are not Newtonian. The most famous one, and you've done this before, at least I have, when you mix cornstarch and water, you create what's called oobleck. This is a non-Newtonian fluid. It doesn't behave like normal. Basically, I believe it's... Oh, ketchup is another good example. Ketchup is a shear thinning fluid. You have to apply pressure to a certain point in the ketchup, and once that certain force is applied, then your ketchup begins to flow. Oobleck is something similar. These are all non-Newtonian fluids. They don't behave like water, oil, or the other fluids that you know to be common in this world. I mean, we're not eating cornstarch mixed with water, so we just don't really see this too often. You have to kind of make it. But this is the most popular example of a non-Newtonian fluid. Ferrofluids, I believe, are non-Newtonian. Ferrofluids are like magnetic particles suspended in a liquid. And then when you apply a magnetic field, you can stiffen up the fluid or you can loosen it up. That would be very non-Newtonian. Mass flow. So well, first off, I'm going to do this before I forget. So now that we're dealing with fluids moving, we have velocity. And so velocity is just going to be v for how I write things. And we're now going to deal with volume, which I put hooks on, so that we can know the difference between velocity and volume. And I have to be careful about that. Mass flow rate is conserved, meaning if I've got a pretty little pipe here, and it's narrowing to a ridiculously small amount, the mass flow rate at one point over the mass flow rate at another point, those are equal. It's not the amount of mass that's flowing through the larger area, we'll call A2, and this we'll call A1, because clearly different masses are going to flow through it, but it's the mass flow rate, meaning a large amount of mass is going to flow through at A2 over a short period of time since it's got a larger hole. But when we get down to this little cranny here, I guess for a lack of a better word, we're going to have a lot less mass flowing through it, but it's going to take longer to go through it. So it's that value, that mass flow rate, that's actually conserved. Now, looking at what I have here, I'm going to kind of express this differently. We remember that mass is density times volume, so I could say rho delta V over delta T. And I also know that, I said I was going to do it, and I didn't, sorry. Volume is area times some sort of height. We'll call it distance in this case. So I take rho, we'll call it delta A for a while. It's really bad, delta A. Let's change that up. There we are. And then we'll call it distance all over delta time. I put this in a specific area because distance over time is nothing more than velocity. And I'll drop the delta for simplicity here in a second, but basically it's going to be equal to rho A V, and that's equal to delta M over delta T. I should have written that there. That's a little bit confusing, so I'm going to rewrite it over here. Sorry about that. So that is another way of expressing your mass flow rate, is rho AV. Now, we know that mass flow rate is conserved, and so what I can do is I can say rho 1 A1 V1 equals rho 2 A2 V2. Well, if the fluid is not compressible, and very few fluids are going to change density because they're not going to change temperatures that drastically, we know that rho 1 is going to be equal to rho 2. And pretty much in all your applications, I think it's like that. And so really, we get an equation of A1 V1 is equal to A2 V2. This is what's known as the equation of continuity. A very weird name. Honestly, I've never thought about it till right now. Mainly because I can't spell continuity. Continuity. Close enough. Equation O continuity. Equation of continuity. And basically it allows you to examine mass flow rate. And that comes up with one other thing, volume flow rate. And so if I just take one side of this, I could say that Q is generally equal to AV, where Q is your flow rate. Sorry, volume flow rate. You probably know from chemistry Q equals MC delta T. It's there. It's here too. This next chapter, but we note it as a volume flow rate. Now, how is that volume flow rate? AV? What the crap you're thinking? Well, or maybe you're not thinking that. Maybe you should be thinking what the crap, because that's what I was thinking when I first saw this. Okay, never not. I don't remember what I thought, but we'll pretend that's the case. Well, okay, so this is a meters squared is the unit for area, and velocity is meters per second. So, surprise, surprise, cubic meters per second. So that's why we call it the volumetric flow rate. The volume flow rate is an area times the velocity. So if you know the area of, say, your pipe and the velocity of the fluid going through it, you can get your volumetric flow rate, which is actually pretty common out there. Even like if you're building ducts or you do HVAC, you have to kind of figure out volumetric flow rate. Unfortunately, they don't use cubic meters per second. They use cubic feet per second, but they still do volumetric flow rate. So, well, we're going to use our equation of continuity on our next problem. All right, doing a problem. Let's say you have a spherical water bladder. A bladder is like a water bottle, except it's plastic, and you can make it real small, and you can take it backpacking, which is what I did. And the internal velocity, it's got a volume of 1.5 liters, and it's got an internal velocity of 0.1. What I mean by that is we assume that it's spherical. We're assuming that the velocity straight in the center is 0.01. If what is the velocity of the fluid if it exits the mouth of the bottle at if it has a diameter of 4 centimeters? And then how long would I have to take to hold a bucket underneath to catch all the water? So, true story, I lost my water bladder somewhere out here in Alaska. We had a little boat plane, and it took off, and it landed on the water and dropped us off, and then they picked us up like 4 days later. I ended up finding it like later on that day, but when I was crossing a stream, it was very cold, and the water was rushing really fast, and it was somewhere way back here, and I lost it. But I later on found it in this lake, so I was happy. Anywho, well, we need to use equation of continuity, which is A1 V1 equals A2 V2. We have the information to find A2. We know what V1 is. That's that velocity, but we don't really know the area. So I said assume it's roughly at the center of the circle, so that I can use. We know our volume is equal to 1.5 liters, which we can't use liters, so we need to get rid of liters. How do we do that? Well, I know there's a 1 milliliter is a centimeter cubed, so 1,000 milliliters, or 1 liter, is going to be 1,000 centimeters cubed. So that at least gets me over to a meter type unit. And then we need to get to cubic meters, and there are 1,000 centimeters in a cubic meter. So you need to put 100, and then you have to cube your 100. And it doesn't look good right there. I'm going to fix you up real nice. There you are. Cubed. And so when you do this, I think you get I need more room here. 1.5 times 10 to the negative third. Now, I need to figure out the area of a circle, but I do know it's spherical and that the equation of a sphere is 4/3 pi r cubed. So I can use this to figure out what the actual radius is. So I take that, multiply it by 3, divide that by 4, divide by the good old pi, and raise that to the 1/3 power, because I don't know where my cube, I don't know where that button is at all. And I get around 7 centimeters, or 0.07 meters. And then area then is just going to be pi r squared. So now I can do that problem. All right, so we have A1 V1 over A2 is going to be equal to V2. And now with that information, A1 is going to be pi 0.07 meters squared, 0.01 meters per second, all over A2, which is going to be pi, diameter of 4, so half the diameter is going to be 2 centimeters, so that's going to be 0.02 meters squared. Now, let's math it up. I'm going to square that little puppy that it's already in my calculator. Multiply by the good old-fashioned pi. Multiply by 0.01. Should just cancel out the pi. Divided by pi. Divided by 0.02 squared. Could have canceled it. Could have canceled it. And I get 0.12. Or let's round it up. 0.13 meters a second. Alright, so I'm able to get a different velocity just by knowing certain areas and certain velocities using the equation of continuity. How long would one have to hold the bucket underneath to catch all the water? So this is where I need to use the fact that Q is equal to AV, and rather it's not A1, it's actually A2, since that's where the mouth is. And so I need to do that. I need to figure out what Q is. So I just take the pi times the radius of 0.02 meters squared, and then times the velocity we just found, and I'm just going to use the 0.13. And that will give me my volumetric flow rate. So pi times 0.02 squared times 0.13 is going to give me 1.6 times 10 to the negative fourth. And that's going to give me cubic meters per second. So that's my Q, right? And we know that all of the water has a volume of 1.5 times 10 to the negative third cubic meters. So if I just take my volume and divide that by my time, I get my volumetric flow rate. Okay, and so I'm just solving for T, so I really just need my volume divided by my volumetric flow, and that's my time. So let's do that. So this is 1.5 times 10 to the negative third cubic meters over 1.6 times 10 to the negative fourth. Cubic meters per second. All right, so 1.5 times 10 to the negative third divided by what's already in my calculator is going to give you about 9.2 seconds. So that's one of the more interesting aspects about this equation of continuity. You can actually figure out how long you're going to need to, say, hold something beneath a hose based off of the velocity and how much water is coming out on the area of that hose, which is kind of fun. So you can use this to make decent predictions. All right. Excuse me. On to Bernoulli. Basically, in a steady state of a non-rotational flow, assuming it's a non-viscous fluid like water, with two separate points, we actually get a massive equation known as Bernoulli's equation. Now, where does this equation come from? Well, let's look at this. We have a beautiful little pipe where water is in one area and rises up to another area and gets to the top there. So let's say we want to know the total energy due to non-conservative forces, WNC. Based off of my little picture here, that's going to be E energy all at 2 minus the energy all at 1. So remembering conservation of energy, so the energy at 2 is going to be mass, the potential energy, so that'll be mass times gravity times H1. Oopsie, H1. Plus its kinetic energy, and it's irrotational, so we don't have to worry about rotational kinetic energy. And so that's going to be 1/2 of mv1 squared. And so that'll give me my total energy there. Oh, I said E2. Those supposed to be 2's. My bad. And then minus my energy at 1. So that's going to be mgh1 plus 1/2 m1v1 squared. So that would give me my total energy due to non-conservative forces. Now, what I want to do is I kind of want to relate this to pressure. So how do I do that? Well, I know that work is force times some displacement of some sort, right? And we also know that force is equal to pressure times area. So I could say that work is equal to um, pressure is equal to force over area. Yeah, I caught that a second ago. Force over area. So I know that my work is then solving that for F is going to be PA times D. Any type of area times some sort of third dimension is going to be volume. And so you can actually express work as pressure times volume, um, which we're going to deal with a little bit more in some later chapters. So, kind of what I want to do is combine these two. Looking at my work due to non-conservative forces, it's actually going to be the change in pressure times the volume, since we're undergoing a pressure change. And to find that delta P, I need to find the change in pressure from higher to lower. So that's actually going to be P1 minus P2. And we put the 1 out front because obviously the pressure is going to be, we want a positive change in pressure, and the pressure is going to be higher at 0.1. So we use that. We could easily flip some other things around as well, but I'm just going off of the drawing that I had. And so I want to set those two things equal to each other. So I will. So that's going to give me P1 minus P2 V equals, fun times now. We've got mgh2 plus 1/2 mv2 squared minus mgh1 plus 1/2 mv1 squared. Notice that I can get rid of my volume if I divide that into each of the masses. So that'll give me P1 minus P2. Well, okay, when I say get rid of it, simplify it, because mass divided by volume is density. That's really what I should have said to be more accurate. So that's going to be rho g h2 plus 1/2 of rho v2 squared minus rho g h1 plus 1/2 of rho v1 squared. And then I could move my whole 1 argument to this side and move my 2 over here to get, positives with positives. And I end up getting the top equation, which I'm going to erase this because it's really hard to see now because I wrote so close to it. Sorry about that. The book uses, I believe, Y's, and I chose H's because that's kind of how we learned conservation of energy. But it really is the same. You can easily substitute H's, and you'll get the exact same setup. So this Bernoulli's equation allows us to find the velocity of a fluid even if it changes height. Whereas equation of continuity, it had to be at the same height. And so this is kind of a step up above the equation of continuity. One other interesting regard from this, come down where, actually I'm just going to erase this. Thought I had enough room, and I did, but not enough for what I want to do right now. So I'm going to erase. Go, eraser. Keep erasing. You're doing a good job, eraser. Just might as well get the rest of this because I'm just going to get annoyed with myself. Okay, so there is an implication of Bernoulli's equation, so I'm going to write that down here. So let's say that you have one side of your equation, let's say, is constant. So let's call this side a constant. Um, okay, so basically put, sometimes the Bernoulli's equation is just expressed as the constant is equal to, say, one side of the equation due to how we created it. Another part of that, or rather implication, is let's say it doesn't quite change heights. Let's say it starts and ends at the same height. And so that would actually reduce to P1 plus 1/2 of rho V1 squared equals P2 plus 1/2 of rho V2 squared. And assuming we're still going with that constant metaphor, if this side, if one of these sides is equal to a constant, so P1 plus 1/2 of rho V1 squared is equal to some constant, then one of the implications of Bernoulli's equation is that if your pressure increases, your velocity of your fluid will have to decrease. And if your pressure decreases, then your velocity of the fluid is going to have to increase. And this is due to Bernoulli's equation. Pressure is higher when the velocity of the fluid is lower, and then vice versa. A good example of that, a partial example of that, really. No, I think it's a good example. Let me see here. www.ucar.edu/weather. Boom. All right, let's look at the current weather map. Come on, Mr. Current Weather Map, pop up. I just want the current analysis. No, well, that'll work for me. Oh, really? That's what you're going to do to me? You're not going to give it big? Oh, we are not friends. I can work with this, though. All right, control. Where's the plus? Because I don't really have it on this. All right. So, a couple things here. Where the lines are really close together on a weather map, that is when you have high speed, so it's a high pressure gradient, means pressure's changing a lot in that area, and so you have high wind speeds. So look around this low up near Hudson Bay. It is incredibly very windy over there. Not as much windy here around the Appalachian areas in this low. It's not quite as strong as this low, which is pretty intense. But do notice that in your high pressure systems, like your high pressure system out here, out in the West Texas, or your high pressure system dominating the Colorado Plateau, your high pressure system in western Montana, high pressure system on the edge of the Great Basin Desert. In all these cases, the lines are very far apart. This is an example of Bernoulli's equation. When we have high pressure, we have a low fluid velocity, i.e. not much wind. But when we have a low pressure system, we have a lot more wind, i.e. higher fluid flow velocity. So that's kind of a good implication, in my opinion, of Bernoulli's equation. And I hope I'm going to have to change that. I had to change the size of my screen. It's going to drive me crazy. All right, doing a problem. First, let me kind of show you what this looks like. So basically, we have a water tower, and it's 75 feet to the ground, and then a total of 90 plus 135, sorry, plus 35 gives you 125 feet to the absolute lowest point. We're going to use that value right there as our base. We're going to measure everything relative to this base. And so this is 125 feet. And then from its lowest point, it goes up 55 feet into a garage. And so we're going to use that too. Now, the problem. Water leaves the water tower pumping station as shown below. Assume the water is pumped out at a velocity of around 3 meters a second and at a gauge, sorry, I spelled that wrong. I'll correct it on the other one. Pressure of 310 kPa. The water comes out of the faucet in the garage around 5 meters a second. What is the water pressure at the garage? So we got to use Bernoulli's equation. And remember that is going to be P1 plus rho Gy1 plus 1/2 of rho V1 squared is equal to P2 plus rho Gy2 plus 1/2 of rho V2 squared. We're looking for P2, so I'm going to pull all this to the other side and pull some things out. That gives me P1 plus rho G, and then that'll be Y1 minus Y2 when I pull it over. And then the same thing, plus 1/2 of rho V1 squared minus V2 squared. And then that's all equal to P2. All right, so now that I have that information, I could solve it, but I need to convert these into meters because it was in feet. So I'd be careful with that. So I take 125 and multiply by 0.309, and that's going to give you 38.6 meters. And that gives me 17 meters for 55, roughly. So we'll use those as our heights. So, not the only way of doing it, just the way I came up with it works. All right, so this will be 310E3 PA plus rho, which is 1,000, G, which is 9.8, Y1 minus Y2, so that's going to be 38.6 minus 17, which is going to give you 21.6. I'm combining some things. I'm going to run out of room. It's a long equation. Plus 1/2 of 1,000. I have to drop my units, so I'm running out of room here. V1 squared minus V2 squared. At 1, it was 3, so that would be 3 squared minus 5 squared. And then that will be it, and equals P2. Equals. All right. Doing some math here. I'm going to start at the right. So that's 0.5 times 1,000 times 3 squared minus 25, 9 minus 25. And then we're going to add that value to 1,000 times 9.8 times 21.6. And then we're going to add that value to 310E3. And that gives me a much larger value. And that's 513. Let's say 514 kPa. It's a higher pressure, but it is at a lower point along the chain, and the velocities and the pipe sizes can be different. And I think one of your problems I give you mentions that the pipe diameters may be different, even though it's on a higher floor, so you're going to have things that are a little bit off. But the point is, we're able to use Bernoulli's equation to predict different pressures at different points based off of velocities of fluids and heights. All right. Viscosity. I've mentioned this before, but viscosity is resistance to flow. And your book doesn't really go into a proof, and that's because there's not really a proof of the viscosity equation. It's generally more experimental. But basically, the tangential force needed to move a fluid layer at a constant speed v over an area A and located a normal, so 90-degree distance from y, from an immobile surface is described by F is equal to nu AV over y. Wow, that's a lot of new stuff. Nu is your coefficient of viscosity, so it shows you how viscous something is. A is area, V is velocity, Y was the surface, the normal distance surface. An ideal fluid would have a viscosity of 0, so you wouldn't need any force applied to it. But fluids are not ideal, clearly. The unit for the coefficient for nu is a poise, which is a Pascal second, which is kind of a weird unit, but that's just basically how it ends up working out. Force is, of course, in newtons. And so the poise is a new thing for you. Clearly different than anything that we've experienced, at least up to this point. And then one thing that we do need to note with respect to poise, which I didn't mention here, is that one poise is equal to 0.1 Pascal second. I really need to change that. You know what? We will change that.